Okay, let's talk about this tutorial number 10. This is a handout. It's not in your published book. It deals with rotational kinematics. And we start with a wheel that is rotating, we're told, clockwise at a constant rate. And we're asked about the linear velocity of several points on that wheel, A, B, and C. Now, linear velocity, of course, is just how fast it's going, according to the speedometer, and in what direction. And so you see that even though they're on the same wheel, A is going around a bigger circle in the same amount of time that B is going around the circle. So I've got a really large velocity for A, and I have a much smaller velocity for B. And point C is further away from the center of the wheel than B, but not quite as far away as A. And so it's going to have a velocity that's somewhere in between. And so I would say that the magnitude of the velocity at A is greater than the magnitude of the velocity at C, which is greater than the magnitude of the velocity at B. And the direction would be tangent to the circle each is traveling. Okay. Now, we're asked to consider what those velocities would look like after that wheel has turned 90 degrees, or 1/4 turn. So if I can draw that wheel again, do my best. A is now going to be here, and B is going to be here, and C is now going to be down here. And this is the center wheel. This is okay, and the wheel's spinning at a constant rate, and so the magnitude of those velocities will stay the same. But now A is moving to the right instead of towards the top of the page, and B is moving down towards the bottom of the page instead of to the right, and C is moving to the left instead of down. So they've all, their directions have all rotated 90 degrees. Now, here's the big takeaway, the big aha of rotational kinematics. For something that's spinning, a rigid body like a wheel, there's not one single linear velocity vector that applies to every point on that wheel. The different points are moving at different speeds and at different directions. Not only that, but as time goes on, the velocity, linear velocity for a single point changes. So the answer to this question, is there a single linear velocity that applies to every point? Not only no, but heck no. Okay? First of all, each point has a different velocity, and the second point is that that velocity changes with time. Now, at the bottom of the page, we're asked to consider the interval of time required for point A to get all the way around the wheel and back to its starting position. And we're asked do points B and C take more, less, or the same amount of time? And I think your gut's telling you that they're all moving around the wheel together. And so if it takes 2 seconds for A to get around, it takes 2 seconds for B to get around and 2 seconds for C to get around. So I would say the time for A to return to its original position is the time for one revolution of the wheel. This is the same for B and C. Okay, that's the first page here, and we'll come back to that first page as we answer some of these other questions. Now, we're asked to consider the trajectory of each of the labeled points as the wheel makes one complete revolution. Do the trajectories all lie in the same plane? Well, the trajectory is just the path that that point follows as it goes around. And for A, it would be a circle that goes around the outside of that wheel. And for B, it's going to be a circle, a concentric circle around the center of the wheel. And for C, it's going to be another concentric circle with a little bit bigger radius. And so those are the three trajectories that the 3 points follow as the wheel goes around. And so my answer to this question, do these trajectories lie in the same plane? Well, yes. The trajectories are concentric circles. Whoops, circles. My bad. Circles in the plane of the wheel. And here's the big point, is I was able to draw those trajectories on a flat piece of paper, on the same piece of paper. And that piece of paper defines a plane. And so we could say that's the same as the paper. Find a vector that could be used to represent the orientation of the plane of the trajectories. Well, if I were to reword this and say, what one vector could you give me? Think of this pen as a vector, with this being the point. If I were to give you a vector and ask you, what plane does that describe? What plane does that represent? And it needs to be a unique plane for each vector. Okay? Now, if I had a vector that is actually in the plane, that doesn't give me a unique plane, because that vector is parallel to that sheet there, but it's also parallel to the sheet when I'm holding it like this. And there's an infinite number of orientations for that sheet that would be parallel with that vector. However, okay, you gotta get it focused again. Focused. That just freaked it out. If I choose my vector to be perpendicular to the plane, then if I handed you a vector, you could immediately put the the piece of paper up perpendicular to it, and that would be the only plane that's perpendicular to that vector. That would be a unique plane. And so we want to choose a vector that is perpendicular to the plane of the wheel, or since we're drawing the wheel in the plane of the paper, it would be the plane of the paper. Now, that's what we found in class, was that when something was spinning about an axis, the only part of that wheel that doesn't change direction as the wheel turns is the axis. And so, as strange as it seems, we're going to define an angular velocity vector, omega, which is along that axis. So we're going to explore that right now. In class, we defined the angular velocity vector, omega, which gives information that applies to all points on the wheel. Every point, A, B, and C, have the same angular velocity, omega, because they go through the same angle, namely once around the wheel, whether you want to call that 2 pi radians or whether you want to call that 360 degrees, in the same amount of time. If the angular velocity vector of a wheel has length 6 pi radians per second and direction straight up towards the ceiling, how can you obtain the following information? Well, first of all, what's the time interval required for one complete revolution of the wheel? Well, we're told that the omega has a magnitude of 6 pi radians per second. Now we can multiply that by 1, and there's lots of ways to write the number 1. I know that 1 revolution is the same as 2 pi radians. And so that's going to give me 3 revolutions per second. Now, let's think about that. I'm going to carve off some space here. If 1 revolution takes, we're told, no, let me back up. If 3 revolutions take 1 second, that's what this is saying here, then if I divide both sides by 3, then I get 1 revolution is 1/3 of a second. Okay? Now, the orientation of the wheel has to be, perpendicular to this omega vector. Well, if the omega vector is pointing up towards the ceiling, then the wheel has to be parallel to the ceiling. Okay. Now, we talked about a right-hand rule for omega. And we said that if that wheel were parallel to the ceiling, and if the omega was pointing towards the ceiling, that's an omega that's coming out of the page, okay, like that, coming up, okay, that we could use our right hand to figure out what direction the rotation was for that wheel. Remember, our thumb goes in the direction of the omega along the axis, and our fingers wrap around in the direction of the rotation. And so this wheel would be, if we were looking down on it, rotating counterclockwise. Okay? Now, let's determine the direction of the angular velocity for the wheel in part A. So the wheel in part A was rotating clockwise, remember? And so if we were to take our fingers of our right hand and wrap that in the direction clockwise that the wheel is rotating, our thumb is, I think it's hard to see, but my thumb is pointing into the page. So omega would be into the page. Does this vector description of the rotation depend on your location relative to the wheel? Which side of the wheel you are on? Well, the answer is no. A vector has a direction that's unique, independent of coordinate system. And so if I were, well, first of all, we found in class that clockwise and counterclockwise just didn't work very well, because if I'm on one side of the wheel and I think it's going clockwise, then you're going to think it's going counterclockwise if you're on the opposite side of the wheel. But if I say the omega vector is pointing north towards Canada, well, it doesn't matter where I'm looking, whether I'm looking south or whether I'm looking north, that vector is still going to be pointing towards Canada, one way or another. Okay. Now, in this bottom activity rather, you see that you're being financially ripped off. That by sending you home, we essentially robbed you. Because if you had come to class in the lab, you would have found that we had purchased very expensive pinwheels for you to play with. And you would use those pinwheels to try to practice with your group, setting up different omegas. And so, for example, if I had a wheel that was turning, I'm not very good at drawing things in 3 dimensions. That's really not very good. Okay, let's try again. Okay, I'm going to try it again. Let's say I had this rotation that was going up and then down the back. Okay, so it's rotating that way. Well, it's rotating about this axis here, and by right-hand rule, if it's rotating like that, the omega vector would be to the left. Okay, and you were going to set up different examples, like an object whose angular velocity points west and horizontal, and here I was using a coordinate system where that was north and that was south and that was east and that was west. And so I would set up my pinwheel so that it was rotating about an axis that was pointing towards the west. Okay, now we know I can't draw. Let's talk about changing angular velocity. We dealt with changing linear velocity in the first part of the class, and we called that acceleration. And we're going to find a quantity that is similar to linear acceleration. We're going to call it angular acceleration. Again, we're going to need to set up a coordinate system. Let's call that direction north, this south, this east, and this west. Assume that we have an initial omega that's pointing due north parallel to the floor. And so since my desktop is parallel to the floor, due north is going to be, I'll draw it right here. omega naught. And then we're told that we make the wheel spin faster and faster so that eventually a fixed point on the wheel is going around twice as many times each second. Well, if it's going around twice as many times each second, it's going through twice the angle each second. And that means the omega is going to double in magnitude. So that means that my final omega, which we're told is also pointing north, is going to have a magnitude that's twice as big as the original and in the same direction. Now, the change vector is what I have to add to this short vector to turn it into this long vector. Well, to do that, I have to add something in the same direction. That would be my change in omega. And you see there's the plus sign right there, where they're stacked head to tail. And so that gives me that the magnitude of that change vector is just going to be the magnitude of my original vector, because I just doubled the length. And the direction, as we can see, is still going to be north. Now, in this second activity, we start with the same initial omega, that's north, but now our final omega is east, but has the same magnitude, the same length. Okay? Now, what you should be seeing there is that I had something rotating like this about an axis, and that gave me an omega naught up, and then a little bit later that was rotated such that the omega was east, meaning it would be by right hand rule rotating like this. Okay, and so we kept the wheel spinning the same rate, but we rotated the axis from north to east. Well, the change vector is what I have to add to the initial to turn it into the final. That's my change in omega there. And I think you can see with Pythagorean theorem that the magnitude of that change is going to be given by the square root of one side squared plus the other side squared. And that's going to give me the square root of 2 times the original spin rate. And so the change is going to be 41% bigger than the original. And the direction, I think we can see by symmetry that this angle is going to be 45 degrees, meaning that this angle would be 45 degrees. So I could say that it's 45 degrees south of east, or when it's 45 degrees, we just say southeast. 45 is the only angle you can do that. It's just as, it's right halfway in between south and east. So we call that southeast. Now, in this next activity, we have an initial omega that is pointing due west. Okay. And we're told that each 1 second, we're told that the omega decreases in magnitude by 8 pi radians per second in 4 seconds. Okay. So what that means is each second I have that omega magnitude decreases by 8 pi divided by 4 or 2 pi radians per second. Okay, so if this was the omega at noon plus 1 second, or 1 second after noon, I would have to add a change in omega that would be 2 pi radians per second. Okay. And that gives me my value of the angular acceleration. It's going to be 2 pi radians per second for each second, and the direction of that would be east, opposite the original omega direction. So in linear kinematics, we define the angular acceleration, that's three lines, by finding the change in velocity vector for any given time interval and then dividing by that time interval. And we understand what that means by plugging in a time interval of 1 second. And then what we find is it's the change in velocity that happens for each second. So from noon until plus 1 second. Well, we're going to do the same thing with angular motion. We're going to define an angular acceleration. Again, that's 3 lines for a definition. It's not going to be the change in linear velocity, but the change in angular velocity divided by how much time it takes. Okay. And we're going to find that many of the things that we found to be true for linear kinematics are also true for rotational kinematics. For example, we found in linear kinematics that when something was speeding up, we had linear acceleration and linear velocity were in the same direction. Well, here, if something's spinning faster and faster, we find that rotational velocity and rotational acceleration are in the same direction. But if it's slowing down, if the wheel has friction or someone's putting their hand on the wheel to slow it down, then those two vectors, omega and alpha, are in opposite directions. Okay? But we find that alpha and change in omega are always in the same direction, just like linear acceleration and change in velocity were always in the same direction. And that's because time always marches forward. Delta t is always positive unless you have a time machine. And so these two vectors will always be in the same direction. Okay. Now the last page of this tutorial is an old exam question. And it involves an Atwood's machine, we call it, but it's just two masses, A and B, that are connected by a massless string, and they're hanging on different sides of a pulley. And in this case, A has half the mass of B, and so if the hand just let go of A, B's going to go down towards the ground and A's going to go up towards the pulley. But that's not what we do in this problem. In this problem, the hand shoves A towards the floor, just gives it a great big old shove, and sends A headed towards the floor. But that's not the direction A wants to go. And so after A leaves the hand, after the hand stops pushing, A's still moving towards the floor, but it's slowing down. As it approaches the floor, it's slowing down. And so the original velocity of A is going to be down, but it's going to be slowing. Whoop, I didn't move enough, so my lights went off. Just a second. Okay, there we go. Now, if A's going down, that means this pulley is rotating from our perspective counterclockwise. And by right-hand rule for omega, that means the omega must be out of the page. Okay, we're asked to find the direction of that angular velocity. And this is while the object is moving down towards the floor. Now we're also asked to find the direction of the angular acceleration. Well, we know that the wheel is slowing, so that means that alpha is opposite direction as omega. And so if omega is out of the page, alpha must be into the page. Now I should have said at the beginning that we're looking at 3 different times during this problem. This first part, we're looking while A is still approaching the floor. At this second time, we're looking at object A at its turnaround point, where it stopped going down and it's about to go up. And then the third time will be while A is speeding up towards the ceiling. So let's look at the turnaround point. We know that if A is stopped, that the wheel is, the pulley is stopped. Well, that means that omega is 0. Okay, you're not turning. Your magnitude is 0. But what about alpha? Alpha can't also be 0. Remember, alpha is how much the omega is going to change in the next second. If alpha were also 0 at the same time omega was 0, that wheel would never turn again. That pulley would just stay put, and A would be frozen in place. So we know that alpha cannot be 0. So we have to look at the change in omega from a little bit before the turnaround point to a little bit after the turnaround point. Before the turnaround, omega was out of the page, and a little bit later it's going to be spinning the other way, so omega will be into the page. Well, if I want to change a vector that's out of the page into a vector that's into the page, I need to add a change in omega that's into the page. Well, remember, alpha is always going to be in the same direction as my change in omega, so that means alpha would also be into the page. Now this should remind you of something. You remember that very first tutorial in 205 a million years ago. We dealt with a ball that was moving up a ramp and then stopped and started moving down the ramp. And we found that at the turnaround point, the linear velocity was 0, but the acceleration was not. We had to take an initial velocity just right before and a final velocity right after the turnaround point. And we had to take these two velocities and put them tail to tail and ask ourselves, what change did we have to add to a vector up the ramp to turn it into a vector down the ramp? And that was the change in linear velocity. Well, that's what we're doing here. It's just harder to visualize because it's three-dimensional, and we're going into the page and out of the page there. Okay, let's finish this up. When object A is moving up towards the ceiling and speeding up, well, if A is going up, now the pulley is turning clockwise, and that means my omega, by right-hand rule for omega, is going to be into the page. And if this pulley is spinning faster and faster, that means that alpha is in the same direction as omega. So it would also be into the page. Now, I want you to notice something. Omega changes from out of the page to 0 to into the page. It goes through a turnaround. But throughout this whole motion, I find that alpha is always into the page. Into the page here, into the page at the turnaround point, into the page when A is going back up. And we're going to find next week that alpha, the angular acceleration, is caused by this thing called torque. And just like linear acceleration is caused by the net force. And that's where we get into rotational dynamics. That's going to be the topic next week, and next week's tutorial, torque. And so throughout this process, as soon as the hand lets go of A, the torque on this system is going to remain the same. And so we can expect the direction of the alpha, which is caused by the torque, to change. That'll make more sense next week. Okay, folks, I hope this has cleared up some of your questions regarding the tutorial. A blessing on your head.